Hello, and welcome to this big set of notes all about momentum and collisions and just practicing the two, right? So I'm going to try to get through as many of these problems as I can, so I'll have to go fairly quickly, maybe not explain quite as much, just so you guys get enough practice. So a lot of these are examples from the textbook, but also I'm going to work out some of the practice problems in the review section that aren't worked out in the textbook too. But I'm just now noticing you should have a paper version of this provided. So if you're in the classroom, it's in the wooden podium where I usually teach from. So you can go get one of those. And all you really have to do, this will give you some really easy points starting the semester off. It's just, take some notes as I'm going through these problems, right? Work them out on a sheet of paper as I'm doing them. There are some extras that I might not get to in this video. That's okay. So it's sort of up to you to finish the rest of them, but I will post the solution guide for whatever problems we don't get to in this video. I just don't want to make this video super long. So I noticed after putting all these problems on this set that I created that actually there's a type of collision problem that you actually should be aware about that's not really reflected in these examples. So I actually want to start off with that because it's actually one of my favorites, but it just doesn't show up as far as I can tell, it doesn't show up in any of these problems. And I have a lot of problems on this page. It's a kind of problem where you have sort of a 2D collision, right? So here we have two, you can think of them as billiard balls, similar mass, right? You could basically think of this as, you're playing billiards. Here's a ball that you've just hit that's going at 10 meters per second. It's going to collide with the second ball. And you guys should know this if you played billiards. They go off at different angles. And the most important thing to point out is that momentum is conserved, which you should always ask yourself why, right? Why is it conserved? Well, think about the forces, right? Is there an external force acting on this two-ball system, right? And keep in mind, this is like a bird's eye view, right? Where there's like a billiard table under these balls, right? So even the force of gravity pulling the balls, that would be going into the screen. There's a normal force coming up out of the screen towards your face right now. So the net force, basically is zero on this system, right? And so one of the balls is traveling at a velocity, and it's just going to collide with the other. So in that case, momentum is conserved. There's not going to be some outside external impulse being added, and we're going to utilize that fact. And you can also see here, just from sort of the after effects, that it's also kind of interesting to point out that this is an elastic collision. And what I learned recently is that if you have an elastic collision like this, what's really, really nice, and you can look this up, this was, I think, a YouTube channel called Physics Ninja. He goes through this whole derivation for an elastic collision like this, and basically gets to the end of his proof and basically proves that sum of those two angles has to always be equal to 90 degrees. Always, for an elastic collision like this. It's a really cool fact. But anyway, the question is, if I know some of this information, I don't know the masses, but I know some of the velocities involved, can I find that second final velocity? We'll just call it V2, right? So how does conservation of momentum play in here? Well, we know, right, in this case that P initial as a vector should equal P final as a vector. Now, you don't really need to worry about the vectors until you get to this after case. And there's sort of two approaches you can take. The first approach is to use this equation and literally start writing vectors in terms of the bracket notations, right, that we learned sometime last semester, right? So stuff like this, right? And you could create equations out of that. I suspect that you guys would prefer a different approach, though. So what we can say is, this is equal to this if the x component of the initial momentum vector is equal to the x component of the final momentum vector, right? These don't have arrows above because now it's just the component, right? It's just a scalar. We also need this to be true, right? The initial momentum y component has to be equal to the the final momentum y component, right? So saying that this is true is the same thing as saying these two things are true. And that might make, the problem a little bit easier. You avoid vector notation. So I would say in a case like this, it's probably easiest to look at the y component, right? This equation. So the initial momentum in the y direction, let's talk about before. That's this case, right? Is there any momentum in the y direction for this whole system? No, right? So literally the left side of this equation is 0. The final momentum in the y direction is going to be this scenario, right? So now we have a component of velocity in the y direction for both of these masses, right? And so we want the momentum in the y direction. So let's look at the first ball, right? What is the y component of its momentum after the collision? It's going to be the mass times the velocity, but it's the y component of this velocity. So this is going to be v1 times sine of 60. All right, so you gotta know your trick, right? Create that little triangle, right? Here's your angle of 60. We're isolating that y component there, right? v1 sine of 60. So this is the momentum going up, right, in the system, and then there's some momentum going down, so we need a subtraction sign. What's the momentum of the second object? That would be this part of the momentum for the second object. And the angle here is 30, right? So this would be mv2 sine of 30, right? So they're going in opposite directions, so we need that minus sign. And notice, right, if I solve this equation, I get mv2 sine of 30 equals mv1 sine of 60, right? And the m's cancel out. So actually, we can solve for this velocity without knowing any of the masses involved. Or we don't have to know the mass, right? The mass is the same for both balls, but we don't care what it is because it just comes out of the equation. And also, we should know what these values are. Sine of 30 is going to be 1/2, v2 times 1/2. And sine of 60 is radical 3 over 2. So v1 times radical 3 over 2. But we also know v1, right? So I should have probably put that in from the beginning, right? So we can plug in that 5 there. So we get v2 over 2 equals 5 times radical 3 over 2. All right, this turns into, well, the 2's cancel, these 2's, and we get that v2 equals 5 times radical 3 meters per second. Beautiful. All right, so this is just a problem type for elastic collisions I want you guys to be aware of. Okay, now let me scroll up to the top of the notes and get started on some of these. So in class, we already went over these two. We didn't have a whole lot of time to get much farther than that. This right here is not a problem. This is just sort of a picture that shows you more of the vector relationships between impulse and momentum. Remember, if there is no net external force, if there's a net external force applying to the system, right, in this case, the system would be considered just the ball here. The golf club is applying a net external force over a small amount of time, and that gives us the impulse, right? But remember, I should, let me move. I should just rewrite this here. So this is force times delta t, right? Remember, it's a vector. But another way to think of it is also just to say that this is just the change in momentum of the system, right? You can see that very clearly here, right? So this is the change in momentum of the system, right? Remember, change in momentum equals the final momentum minus the initial, right? And when you do vector subtraction, you get those triangles there. So it would be pointed from the end of the initial momentum vector to the end of the final momentum vector. So that's just something I wanted y'all to be aware of. Okay, let's start here. We have a ball of mass 0.25 kilograms rolling to the right at 1.3 meters per second. It strikes a wall and rebounds to the left at 1.1 meters per second. The question is, what is the change in the ball's momentum? So the ball is considered the system. So here it is, 0.25. It's going to the right at 1.3 meters per second. Here's the ball, the wall. And then afterwards, the wall is here. The ball has bounced off of it, and now it's going to the left at 1.1 meters per second. Of course, it has the same mass. So the change in the ball's momentum. We shouldn't need any vectors for this one, right? So change in momentum is final momentum minus initial momentum. Keep in mind, right, the direction of velocity will tell us positive or negative. So the final momentum is 0.25 times negative 1.1 meters per second, right? Because going to the left, the initial momentum is 0.25 times positive 1.3. And so this is something that, let's just put it into the calculator. Negative 1.1 minus 0.25 times 1.3. All right, so it is giving me negative 6e to the negative 1, so that's negative 0.6. And the units would be kilograms times meters per second. Do not forget your units. Do not forget the units. Okay, that's a pretty quick one. All right, here we have another sort of force versus time example. We have a 150-gram baseball is thrown with a speed of 20 meters per second. It is hit straight back towards the pitcher at a speed of 40 meters per second. So the impulsive force of the bat on the ball has the shape shown, right? So the bat is applying a force which increases very, very quickly and then decreases very, very quickly as the ball leaves the bat. What is the maximum force that the bat exerts on the ball? And then what is the average force, right? Now, when you see average force, we might even be able to answer that question first, because the average force, if the force is changing over time, the average force times that time interval is what is equal to the impulse. But we remember that this is also equal to the change in momentum, right? So if we can find the change in momentum, notice how we have the change in time, and we can find that average force. We might deal with the maximum force later. You might be able to find the maximum force, from the beginning too, but I just prefer to do it this way. So what is the change in momentum? Change in momentum, right? Final momentum minus initial, always. Final momentum. So if we consider towards the pitcher the negative direction and away from the pitcher the positive, we would say that, make sure you're using SI units, right? So let's call this 0.15 kilograms times the velocity. The velocity final is 40 meters per second to the pitcher, so that's negative 40 meters per second, right? We might even want to draw a picture, right? Here's the pitcher. Here's sort of the batter. Oh my gosh, that's a terrible bat. You know what? Let me just draw the person, right? So the batter is here. And he's got the, I don't know, the helmet and the bat. Oh, my pictures are really terrible. It's okay. Okay, that's not too bad, right? So positive plus x, and we got negative x. Okay, here we go. So that's final momentum. Then we have this minus sign, and then initial momentum, 0.15 kilograms. And then times, the speed is 20 meters per second. That would be positive 20 meters per second. So what is the change in momentum? All right, calculator time times negative 40. And then we'll have minus 0.15 times 20. Okay, this is giving me a really nice answer. This is giving me negative 9 kilograms times meters per second. Now, I suspect that really all we care about is the magnitude. So really, I guess, as long as we have the 9, right, we know that's the size of the impulse. And then we know delta t. You might want to turn that delta t into SI units, right? So milliseconds. So this is 0.6 times 10 to the negative 3 seconds, right? So the way we would write this would be 0.0006 seconds. So that's our delta t. Now we can actually make use of this relationship on the left. Average force times delta t, 0.0006 seconds, equals our change in momentum or the magnitude of it, right? So we might want to, just to be clear, right, that's kind of what I'm doing here. This would be equal to 9 kilograms times meters per second. So notice how the units actually match up here. So what is the average force? All right, it's going to be 9 divided by 0.0006. That's 1.5 times 10 to the fourth, so that's 1.5123 newtons. So that's the average force. All right, and here's something to think about. The average force should be some sort of force between 0 and the maximum, such that the area of this rectangle is exactly equal to the area of the triangle, right? Because that's the actual impulse is the amount of force times the amount of time. Well, if the force is changing, right, it's going to be different at different times, and so you can think of it as adding up a bunch of really small impulses to get that green area. But the blue rectangle and the green triangle should have the same area. So what that means is the impulse of 9, right, that's the blue rectangle, should equal the green triangle. So 1/2 times base, 0.0006 seconds, times the F max. But notice, right, we already did 9 divided by 0.0006, that was 15,000, and now we're just multiplying by 2. So really, the maximum force is just twice the average force. That's not always true, but it was true in this very simplistic case, right? It's kind of an interesting problem. All right, let's keep going. Okay, so we have a 100-gram rubber ball. It's thrown straight down onto a hard floor so that it strikes the floor with a speed of 11 meters per second. So here's the ground, here's the ball, 11 meters per second. And I'm going to put in kilograms, right? So 0.1 kilograms. And then we have this sort of force versus time graph. Okay, cool. Estimate the height of the ball's bounce. Okay, Estimate the height of the ball's bounce. Well, I believe this is talking about after it hits the ground, how high does the ball go up above the floor, right? So it's going to hit the ground. It's going to have some velocity going up, which we don't know, right? Still the same mass. But of course, right, eventually that ball is going to end up here at some maximum height, this is what we're trying to find. Now, if you remember your kinematics, you guys know that if we find this, we could probably use a kinematic to find that, right? So let's focus on finding the velocity after this impulse. And if impulse is change in momentum, right, J equals change in momentum, then if we find the impulse from this graph, that will probably help us find the velocity over here, which will help us find the height. So you want to sort of see, how the graph sort of, what is the path from this impulse from the graph to the answer that we want. So ideally, the area under this graph is the impulse. In a case like this, we don't really know, it's a curvy graph, but we can essentially approximate it as sort of like a triangular shape, right? So essentially the area under this triangle, the idea is the area under that should be more or less equivalent to the actual true impulse to the reality. You can even tell some of the area of this triangle sort of goes over the graph and then some of it goes under. And you can imagine like the over approximation and the under approximation sort of cancel each other out in the grand scheme of things. So let's find that impulse. J equals, well, in this case, we can calculate it directly because we have the height of the triangle, right? And we have the base. So we don't need to worry about average force. So this can be 1/2 times base, right? So that's going to be 0. Let's do it in seconds, 0.005 seconds, right? There's 1,000 milliseconds in a second times 800 newtons. Cool. And that's going to give me an impulse of 0.005 times 800 divided by 2. It's going to give me 2 kilograms times meters per second. I know we have newtons, right? But remember, newtons times seconds is the same as kilograms times meters per second. Awesome. Okay, so that's our change in momentum, right? So remember, change in momentum equals the final momentum minus the initial. This is the next equation that will sort of unlock the velocity, right? Because we have this. We have the change in momentum, right? So that's 2. The final momentum is going to be that mystery velocity times 0.1. So 0.1 times v. And then we have minus, what is the initial momentum? That's going to be 0.1 times negative 11, right? The velocity is going downward. Positive direction, negative direction. Okay, cool. So we can solve for v. 2 equals 0.1 v. Then we get plus 0.1 times 11. It's 1.1. Right, this is going to be 0.9 equals 0.1 v. V equals, looks like 9 meters per second. I'm writing backwards here, but that's okay. So that is the velocity of the ball going up after it's collided with the floor. And now we want to use some kinematics here. Okay, what kinematic is going to help us? Well, it's going to be this one, right? Change in y equals v0y times t. Oh, wait, you know what? We don't have time. We do not have time. So we have to use a different kinematic, right? It would be vy final squared equals vy initial squared plus 2ay delta y, right? We have all of those quantities. Okay. The final y velocity will be 0. And we have just found the initial y velocity, which was 9. We have plus 2 times, let me go ahead and just use negative 9.8 just to be more accurate. Right, that's going an acceleration going down. And then our delta y, that change in y would be h. Nice. So notice, let's see what we get here. 2 times 9.8, that's going to be 19.6 h equals 81. So that means h equals 81 divided by that number gives me 4.13 meters, roughly. Awesome. Cool. So yeah, that one actually took a lot of work, and we had to work in a kinematic at the end. Okay, so keep in mind, those kinematics are not going away. Let's do these ice skaters, maybe. 2 ice skaters, Sandra and David, stand facing each other on frictionless ice. Right? So they're like this. On some ice. Sandra has a mass of 45 kilograms. And David a mass of 80 kilograms. They push off of each other, right? So they exert equal and opposite forces. Right? After the push, Sandra moves. Right, so Sandra's the 45 kilogram one. Right, so after the push. So after. She's moving off at a speed of 2.2 meters per second. Right? And what is his speed? V. So this is a very nice conservation of momentum. We know momentum is conserved because all other forces external to this two-person system essentially cancel out, right? Their gravity forces and their normal forces have canceled. There's really no friction on the ice, right? Essentially negligible, right? So momentum is conserved. So change in momentum equals 0, right? Or another way to say it, P initial equals P final, right? Now, P initial was 0. So what is P final? Well, let's do David, right? So that's going to be 80 kilograms times positive V. And then we're going to have plus 45 kilograms times negative 2.2, right? Because she's going the other way. So what do we get? We get that V equals 45 times 2.2 divided by 80. 45 times 2.2 divided by 80. So that gives us an answer of 1.2375 meters per second, right? So that's the speed of David. And we should expect this number to be less than the speed of Sandra because David has more mass, right? So if the same force is applied to a heavier object, it's not going to accelerate quite as fast. If you get a bigger number, you know you've done something wrong. Okay, cool. Now I might start picking and choosing certain questions. Remember, these purple examples are already worked out in your textbook. You can look them up. Let's see. Let me look at maybe some of these here. These are not worked out in your textbook, so I might jump here. Let's do the curling one. Curling is a sport played with two 20-kilogram stones that slide across an ice surface. Suppose a curling stone sliding at 1 meters per second strikes another stationary stone and comes to rest in 2 milliseconds. Approximately how much force is there on the stone during the impact? During the impact. Interesting. Curling stone sliding strikes another station. Oh, I see. because I was thinking, well, wouldn't we have to use a kinematic, but then the ice doesn't have any friction, right? Like, so how is this stone coming to rest? The idea is, right, here's a 20 kilogram stone. It's going at 1 meters per second, and here's the other one. And the moment they're in contact, right, 20 kilograms, right, this is the moment where they're exerting those equal and opposite forces, right? And that moment, it lasts 2 milliseconds, right? So it's a very short amount of time, in which case, after that moment, the first stone is now stationary, and the second stone is now going off with some speed, right? Which I'm not even sure we even need to know what that speed is. Or actually, no, we can figure it out almost immediately, right? If we just think about it, momentum initial equals momentum final, right? The final momentum was 20 times 1. Or sorry, the initial momentum was 20 times 1. So the final momentum has to be 20 times 1. And if the first block is stationary, right, then that means the second block is going off at the same speed the first block had, right? And if you've ever watched curling, that actually is exactly more or less what happens, right? Okay, so the question is, how do we find this force here, right? So let's think about this, right? Let's assume that the force is essentially constant. That force is acting on the first stone to the extent that it's changing its momentum, right? So it might actually be better to consider this first stone as being just a system in itself, right? And the second stone is exerting an external force on the system, right? So if we say this is our system, this system does change its momentum, right? The momentum change, right, P final minus P initial, is non-zero because of that external force. Final momentum is 0. Initial momentum is 20 times 1. Right, this is our change in momentum, right? Negative 20 kilograms times meters per second. And that change in momentum should be equal to the impulse, right? So negative 20 kilograms times meters per second should equal the force exerted, which notice that force vector is going to the left, right? Times the amount of time, 0.002 seconds. So what is this force equal to? And remember, we only care about the magnitude in this case. It doesn't really matter the direction as much. So let's just take 20 divided by 0.002. And we get exactly 10,000 newtons. So that was answer choice D. Oh, wow, I took up a lot of space here. All right, so let's see if I can move this up. Oh. It's okay. We'll just draw little fences around our work here. So this was for number 19. Number 20. 2 balls are hung from cords. The first ball of mass 1 kilogram is pulled to the side and released, reaching a speed of 2 meters per second at the bottom of its arc. Right, so we want to think of that 2 meters per second as the velocity it has just before it hits the second ball. So we don't need to worry about how it's accelerating or anything. That math gets pretty complicated. So these balls are very, very close. Very close. Then, as shown, it hits and sticks to the other ball. Right? What does that signal to you? Inelastic collision. Right? So this is not quite a Newton's cradle sort of situation. This is maybe 2 clay balls, right? Where the clay kind of sticks and the balls travel together, right? So what is the speed of the pair just after the collision? So we have some sort of velocity here, which we don't know. if just after the collision is... Oh, sorry, they tell us that. They tell us the speed. My bad. The speed of the pair just after the collision, right, this velocity is 1.2 meters per second. Okay, cool. And we should also point out this speed is 2 meters per second. Awesome. What is the mass of the second ball? Okay, interesting. So we'll just call that mass m, but we know the first ball has a mass of 1 kilogram. 1 kilogram. This is for number 20. All right, well, we know even in inelastic collisions that momentum is conserved. How about we just look at, initial momentum equals final momentum. Let's just see what happens if we analyze this situation. Initial momentum, we get 1 kilogram times 2 meters per second for the first ball. The second ball has a momentum of 0. For final momentum, it's probably best to just treat this as one object, right? And that one object has a velocity of 1.2. What is the mass of that one object? It's 1 plus m kilograms, and then times the 1.2 meters per second. Okay, cool. In fact, let me just get rid of the units here, just so it makes it a little bit easier to see, right? So what we have here is 1 times 2, that's 2, equals 1 plus m times 1.2. If you solve for m, you get 2 divided by 1.2 minus 1. And let's see how much that is. 2 divided by 1.2 minus 1. That is 0.6 repeating. So we'll just say 2/3 of a kilogram. Nice. A very quick one. So inelastic collisions here. Let's do 21. The figure shows 2 blocks sliding on a frictionless surface. Eventually, the smaller block catches up with the larger one, collides with it, and sticks. Right? So again, we have an inelastic case here. What is the speed of the 2 blocks after the collision? And notice they don't give us any numbers. Right? So we just got to rely on the conservation of momentum and let it guide us. Right? We know that momentum is conserved here. All right, so initial momentum is going to be m times 2 vi, and then so that's of the first block, and then plus 3m times vi. That should equal the final momentum. So if they're stuck together, we'll have a total mass of 4m. And then we're missing the velocity of this new thing. Right, so what is the speed of the blocks after collision? So we'll just call this just v, right? Okay, so we have 2mvi plus 3mvi. Ooh, those go together. And over here we have 4mv. In fact, all these masses go away. That certainly is nice. We can just divide by m everywhere. Over here we get 5vi equals 4v. This means that our mystery velocity is 5/4 of vi. 5/4 of vi. That's answer choice D. So you're going to notice this happen a lot in conservation of momentum. Usually the mass, a lot of the time, actually, it'll just fall out of the equation, especially if you're given the proportions of the masses, right? So like this object is 3 times the mass of this one. If you see something like that being described, chances are that mass will come out of the equation. So that's nice. Let's look at 22. 2 friends are sitting in a stationary canoe. So canoe. Draw my canoe, my two friends. Cool. The person at the front tosses a sack to the person at the rear. Oh, yeah, we've done this one, sort of, in class, right? So we're tossing a ball here, or I guess a sack for some reason. So they catch it 0.2 seconds later. Which plot shows the velocity of the boat as a function of time? Okay. Positive velocity is forward. Ooh, that's important. Positive velocity is forward. Negative velocity is backward. So where did they first throw the sack? The person at the front tosses it to the person in the rear. So it's going towards the rear, right? So let's say this is the rear, and that's the negative direction, right? This is the positive. Because that's what they said, right? Positive velocity is forward, negative velocity is backwards. So the ball is going from the ball is moving to the left, right, in this picture, right? So its velocity in the graph, at least, well, let's just stop right there and think about the velocity of the boat, right? I'm getting confused here. Neglect any drag force. Cool. So the the ball gains momentum, a negative amount of momentum. Which means the boat needs to gain, right? So the red is the ball. Let's make the boat blue here. The moment the first friend throws the ball, he provides an impulse to the ball, and the ball provides an impulse to the friend as well as to the boat, right? Because they're sitting in the boat. So the boat should initially start moving forward in the positive direction. So if we look at our graphs, any graph that gives us a negative velocity is wrong. So that's wrong. This is wrong. So really the only options are either A or D. And I guess the question is, right, does the boat go back down to its initial velocity of 0, or does it, continue moving at least a little bit even after he catches it, right? So what is the answer here? What is the answer? Well, if you think about it, right, what we learned about kinematics, right, whatever velocity the ball starts with, we proved one day in class that the velocity here will be the same magnitude for the friend who catches it. Which, if you think about it, means that it's going to require this friend to provide the exact same deceleration as this friend. And if that's the case, right, he's providing the second friend is providing the same impulse as this friend over here. Now this friend used it to accelerate the ball, the other friend is using it to decelerate the ball. But now that impulse, so the impulses between the two friends, we might call them J1, J2, should be equal and opposite, right? And if that's the case, the momentum gained after throwing the ball, right, the momentum gained of the boat should be perfectly canceled out with the momentum lost when this friend over here catches it. So it is answer choice A. But you have to sort of think through all of those things. Okay. Now we have a whole series of problems here. I might only get the time to do maybe a few of these things. So I might try just a few examples. Let's maybe try this one. Number 15 is kind of interesting. And let's see. Maybe I'll do this one. We'll see. A 2.7 kilogram block of wood sits on a frictionless table. Got a block of wood right there. Oh, and I need to label the mass, 2.7. All right, a 3-gram bullet fired horizontally at a speed of 500 meters per second. Okay, 500 meters per second. I'm going to convert this to kilograms, right? Let's keep it all in SI units, 0.003 kilograms. And it goes completely through the block, emerging at a speed of 220. So this is before. And then, again, we're on the frictionless table here. We have after, right? So the block is now probably moving with some velocity, right? So we'll call this VB for velocity of the block. The bullet has gone through the block. Now it's at a velocity of 220 meters per second. Cool. What is the speed of the block immediately after the bullet exits? All right. So let's think about it. Is momentum conserved? Is P conserved? The answer is yes. Woohoo! Why? Well, the only force that could act on either of these objects, other than gravity, which, again, if this happens in such a small amount of time, that impulse provided really isn't going to change the system. In fact, we're considering, right, that the bullet is basically, oh, can't do that. The bullet is, we're considering right before it hits the block and right after. So even my pictures are misleading. But even considering friction, there is no friction. So that's the only other external force that could act on these two objects. So the question is, what is that final velocity? All right. P initial equals P final. Initial momentum. So the bullet has 0.003 kilograms times 500 meters per second plus 2.7 kilograms times 0 meters per second, right? So this whole thing will go away. Final momentum, we get the bullet, 0.003 times 220 meters per second plus 2.7 times mystery velocity VB, right? All right, so let's see what we got. In fact, I can simplify it this way. Let's subtract this term on both sides. So we'll get 500 minus 220, just doing a little algebra trick. And then, of course, the next step would be to divide by 2.7, right? So that's velocity of the bullet. So let's see what we get. We get 0.003 times 500 minus 220 divided by 2.7. We get a velocity of 0.311 meters per second. Again, always make sure your units match up on both sides of your conservation equation. So you have to convert that to kilograms because this is in kilograms. Otherwise, you're going to get crazy numbers, really crazy numbers. And you know, this number actually, it kind of makes sense, right? The bullet is super, super light. So even though it's going fast, it's not really providing a whole lot of momentum, right? So if we just calculate just that number, the momentum of the bullet, it's only 1.5 kilograms times meters per second, which is not a whole lot. So, and that's the maximum amount of momentum it can even transfer to the block. Notice how it didn't even transfer all of that, right? 0.003 times 220. All right, so this is about 0.66. So if you think about how much momentum the bullet lost, whatever it lost has been transferred to the block, and that's not really a huge difference, right? So like 1.5 minus this answer. So the block gained only 0.84 kilogram times meters per second. So you can analyze where the momentum is going, what objects they're being, applied to, because sometimes you can have 3 objects in a collision, right? So the momentum of that 3-object system should still be the same, and you can actually kind of see where the momentum goes. So that's kind of a cool thing to do. So this was for number 15. Let's put a little fence around it. Let's try number 17. So number 17. A 10,000 kilogram railroad car is rolling at 2 meters per second when a 4,000 kilogram load of gravel is suddenly dropped in. Right, so this is our railroad car. So it's already 10,000 kilograms, and it's going 2 meters per second. So this is before. And then, of course, the gravel is dropped in very suddenly. So this is a very quick collision, if you will. All right, so railroad car. Now, what is the total mass? In fact, we might even draw like the gravel here. The total mass is 10,000 plus 4,000, so 14,000 kilograms, right? And now it has some sort of new velocity. It's saying what is the car speed just after it's loaded, right? So there we go. Conservation of momentum, right? So the initial momentum equals 10,000 times 2 meters per second. And this is final momentum is 14,000 times v. So those should be equal, right? So 20,000 should equal 14,000 times v. V should equal, it's just 20 divided by 14, basically. That's 1.43 meters per second, right? Cool. And that should be exactly what we should expect. The velocity should slow down. If you think about it, it's because the force of the cart has to press against the gravel, apply a force to it to accelerate it so that the gravel is going the same speed as the cart. But at the same time, the gravel is pressing on the cart and slowing it down. So eventually, as the velocity of the cart slows down and the velocity of the gravel speeds up, eventually they match each other, and then there are no internal forces sort of accelerating the situation. And this would be a good example of an inelastic collision, right? Anytime 2 objects sort of stick together, that's typically what we call an inelastic collision. Wow, I'm taking up a lot of room with these. Maybe let's try to do one more. In the solution guide, I'll compress all this a little bit better. And let's see. Let's try something. Let's do the dog in the canoe here. It's kind of an interesting one. Number 20. All right, a 9.5 kilogram dog. I like dogs. So we got dog here. There's our dog. Yeah, that works. 9.5 kilograms. Takes a nap, wakes up to find the canoe has drifted out onto the lake, but is now stationary. So there's no velocity here. He walks along the length of the canoe so the dog is walking 0.5 meters per second relative to the water, right? So that might be important later. So I'm going to put black for relative to the water, 0.5. Or no, you know what? Let's do blue, right? That actually makes more sense to me. 0.5 meters per second. Cool. And the canoe simultaneously moves in the opposite direction at 0.15 meters per second. I think they're implying here that it's moving relative to the water that fast. So I guess the relativity part maybe doesn't matter. What is the mass of the canoe? Okay, interesting. So this is happening. This is a snapshot in time, right? The dog is moving this fast, the canoe is moving this fast, and we know the mass of the dog. And we know in this entire interaction that momentum is conserved. There will be very few times when this isn't conserved, really. So anyway, initial momentum. Well, okay, yeah, let's think of it this way, right? Initial momentum and final momentum, right? This is sort of like the final state, right? The initial state was when everything was stationary. It's very easy to see what the momentum would be. It would be 0 initially. And now things are moving. The dog is moving, the canoe is moving. And so there's some momentum, but it should all cancel out to 0. So we have 9.5 kilograms times 0.5. And then we have plus the mass of the canoe times negative 0.15 meters per second. And if you solve this, very quick calculation, this should be 9.5 times 0.5 divided by 0.15. And let's get this final answer here. 9.5 times 0.5 divided by 0.15. I'm getting an answer of 31.67 roughly kilograms. So that is apparently the mass of the canoe. Awesome. Okay, so be on the lookout. I'll work out the others. I'm running on Steam here, so I'm not confident that I can just wing it and answer all these correctly. So I'll make sure to take my time and also organize all these answers here. And you guys can check the answers at another time. So I hope you learned a lot, and keep in mind, right, that this sort of scenario could also exist too for momentum type problems. So I just wanted you to be aware of that. And then we have a lot of other sort of more simple cases. I thought this would be a good unit to start the semester because it is pretty straightforward. In a lot of cases, you're just relying on this fact, right? In a lot of cases, the momentum is conserved. And then in a few cases, right, there's some sort of extra impulse delivered to the system. Like a good example was this one, right? A floor or a wall or a baseball bat is delivering an impulse to something, and you're using that impulse to discover something about, right, the momentum of one of the objects. And really, those are the only two, broadly speaking, types of questions that you get. The inelastic and elastic sort of aspects of momentum really start to shine when we start talking about energy, and we're not there yet. So really, just broadly speaking, if you can categorize something as elastic or inelastic, that's really the only kind of, conceptual style question I could ask you. But yeah, make sure you know how to use the conservation of momentum, or how to recognize if an impulse is being delivered and how to use that impulse. So I'll go ahead and stop it here. I've been going on way too long. Good luck, guys. Definitely do that FRQ with maybe a partner or maybe another person, right? Work on it individually, but then swap papers to grade it. The only other thing posted too as an assignment is that AP Classroom. So that's due Sunday, right? But if you're really smart, if you're going to be smart about it, you should do it before the quiz, because obviously those are really great questions having to do with momentum situations. A lot better than a lot of questions I could come up with. So if you understand those, you're going to be just fine for the quiz. So anyway, take care. I hope this helped. I'll see you guys hopefully, looks like either Thursday or Friday. And yes, remember there's that quiz on Friday. That's not going to magically change. So be productive, be wise with your time. Take care.